Hello again, gentlemen. As you would have seen, we are still doing functions. This is our third session. And perhaps just a step back to ask the question again, what are functions? Well, mathematically, a function can be defined as if it's a function of f in two different sets, we want to try and map set A onto set B with a rule that assigns each element in set A exactly with one element in set B. The set A is called the domain, or the inputs, and set B is the range, or the outputs. From our first lesson, you would remember also that functions are a subset of relations, and we knew that not all relations could be defined as functions. Today we're going to start looking at an inverse function. The inverse function undoes what the original function was doing. We could probably say it reverses it, although I would be hesitant to use those words, but it is the mathematical way of undoing what was done by the original function. So a mathematical definition then of an inverse is that the inverse of a function reverses another function. If we had some function called f applied to an input variable x and it gives a result of y, then applying the inverse to another function called g with its y values will map back onto the original x values and vice versa. So quite technically we could say that if f of x equals y and g of y equals x, then what we know is that if I place f into g, I would be able to get an identity of an inverse. So if we had two functions, one called f and one called g, if I placed g inside of f and the result was x, or if I placed f inside of g and the result is x, then these two functions are inverses of each other. This really is a mapping of the relationship that when y equals x, it would make sense that x equals y. Some functions do not have inverses. Many to one functions that you saw last time do not have inverses, which are functions. Let us consider these two straight lines, the blue line and the red line. The blue line and the red line meet at another special important line called y equals x. The y equals x line, the dotted line, is running up on the 45-degree line through the Cartesian plane. And everywhere that x equals 1, y equals 1. Where x equals 2, y equals 2. So y equals x on this line. What we also notice is that the blue line over here, which has the coordinates of x equals 1 and y equals 3, is mirrored to this point over here, where x equals 3 and y equals 1. What have we done? We have swapped y and x. Let us take a red point and reflect it over the y equals x line. Let's take this point down here. This is the point where x equals 1 and y equals minus 3. The mirror, or the reflection of this point, is shown on the other blue line, and that would be the point here, where x equals minus 3, and y equals 1. X and y have changed positions because x equals y, as we have seen at the top. We need to be very careful when we speak about these inverses. The red function, the parabola that you can see, sketched at origin, if I had to reflect it, would be mirrored over the y equals x line on this side. The problem would be is that I would have a many-to-one relationship. An inverse of this is not a function. Therefore, the domain of the original must be restricted. We will either ask to look at the negatives of the x-axis, the numbers to this side, or we could be asked to look at the positives of the red one, the numbers to this side. What we notice is that if I only focused on the inverse of the green line, it would be this blue line, because every point on the green line, or the right-hand side of the red, is now mirrored by the blue. Even complex cubic functions have inverses. The inverse of f of x power 3 plus 2, shown in red, is mirrored by the inverse f to the minus 1 of x shown in blue. Even the functions you saw last time, a 1-to-1 where every y value has a unique x value is also reflected on the y equals x line, and it is also a function. The same is true for this cubic. A 1-to-1, every y value is unique on this side, and the reflection of this is also a unique function. Look at how beautiful this function is. The red line, which is y equals x to the power of 3, has an inverse described as the cube root of x. Both of these are functions. What about these two? The function on the left is an exponential function and would normally be described as y equals a b to the power x. It is a 1-to-1 where every y value has a unique x value. The inverse function of the exponential function is what we will call a log function. More about logarithms later on in this series. Algebraically, we would like to find the equation of an inverse. Let's assume we start with f of x equals 3x, the straight line. If we know that all inverses are mirrors about the y equals x line, then what we do is we could say that if f of x is equal to y, what we know is that therefore y must have been 3x. But because they are mirrors of each other, we are going to swap the x and the y because y equals x. So our new function, when we rewrite it, will be that x equals 3y. We now want to make y the subject. If we divide both sides by 3, we land up with x over 3 equals y. But we don't want to use the letter y as we saw in our first series, so we give it its inverse name, and the inverse name is shown as f superscript 1x. That tells us we now have the inverse. Therefore, the inverse of f of x equals 3x is described by x over 3. It is the reverse operation. Instead of multiplying by 3, as you can see here, we're dividing by 3, the reverse operation. What about this function, f of x equals minus x, another straight line? Well, we know that we always want to mirror on the y equals x line. So, if we know that f of x is the same as y, we could write it out as y equals negative x. We now want to swap the y with the x because y equals x. So we write out x equals minus y. If I now make y the subject, I divide both sides by the negative and I land up with negative x equals y. But we do not want the y as a name, so we then give it its inverse name. F to the minus 1 of x is the inverse of f of x. This is a peculiar one because its inverse is the original, which is quite beautiful actually. In these straight lines, you can see that if f of x equals x minus 3, I've already sketched its inverse, and beautifully it runs parallel to the y equals x line. Let's look at what its equation is. We know that the inverse runs on y equals x, and that's true because if f of x equals y, we could write that y equals x minus 3, the original function. We now want to swap the y and the x because y equals x. And so what we land up with then is that x equals y minus 3. If I make y the subject, I will have x plus 3 equals y. I do not want to use the letter y, so I'm going to give it its inverse name. X plus 3 equals f of minus 1 of x. So therefore, the inverse of f of x equals x minus 3 is f of x is x plus 3, the parallel line. Let us look at this parabola. It is a parabola where we are only looking at the positive x values. We can see this on the graph when we look at this component over here. It is only the positives of the original function. So if I was going to apply the rule and I knew that it was a reflection on the y equals x line, I could say that f of x is equal to y. So therefore, y is equal to 2x squared. However, what we want to do is swap y with x because y equals x. And so I could rewrite it out as x equals 2y squared. I would divide both sides by 2 and land up with x over 2 equals y squared. And then what I want to do is take the square root of y. But it's important that I notice that I'm only worrying about the positives. So I'm only worrying about the positive result of x over 2 from y. And therefore, we could conclude that x over 2 is the inverse of the original function. What do we notice here? The original function is the negative of the parabola. It would normally be sitting below the line where the red is. However, what we have done is restricted it so that we were only worrying about the positive inputs. What we notice is that when we worry only about the positive inputs, the inverse is this blue line that gets created. So if we were going to do the mathematics behind finding the inverse, we would say that y equals x is where we're going to mirror. F of x is the same as y, so therefore we could write that y equals minus x squared. Again, we want to reflect y with x because we know that y equals x. And so we can say that x equals minus y squared. If I divide both sides by the negative, I land up with minus x equals y squared. And what I want to do then is take the square root on both sides. So if I take the square root on this side, I will end up with the square root of negative x equals y. And therefore, what I know is that the square root of negative x is the inverse of the original. Some of you might be worried about having the square root and a negative, but remember that what you're going to be doing in this function down below is using the inputs of the blue. And what you notice about the inputs of the blue is they are all negative x values. So if you place a negative x next to that negative, the negative with a negative makes the positive, which is allowed in the square roots of numbers. Let us take the inverse of f of x equals x squared plus 1, a parabola that is shifted 1 unit up. What we know is that we're going to reflect on the y equals x line. So f of x is equal to y, and therefore our y that we're going to manipulate is y equals x squared plus 1. What we want to do is swap y with x because y equals x. And so when we write this out, x equals y squared plus 1. And when I solve for y, the minus 1 from both sides, and what I'm going to do is square root both sides to make y the subject. Therefore, the inverse of our original is described by the square root of x minus 1. Let's do this one as a thinking exercise first. We can see here that we want to subtract 5 and we want to multiply by minus 2. So the inverses would be, if we wanted to subtract 5, at some point we have to add 5. And if we were going to multiply by minus 2, the inverse would be divide by minus 2. Let's see if the maths confirms this. We know that we're going to solve y equals x, because f of x equals y. We could write out the original function as y equals minus 2x minus 5. We know that we want to invert y with x because of this relationship. And so what we get then is that x equals minus 2y minus 5. If I add 5 on both sides, I am left with that, and I have to divide by 2. So x plus 5 divided by minus 2 equals y. So therefore, our inverse is described by x plus 5 divided by minus 2. We were expecting this. We could see that because we had a minus 5, the inverse would have to have a plus 5. And because I was multiplying by minus 2, I would have to have divided by minus 2 to undo the original. To be able to work with exponential functions, we need to introduce some new language. And the language we have to deal with is going to allow us to detach the power of the variable from its base. Again, we will start with the understanding that y equals x is our inverse line. And so if f of x is equal to y, we have a function where y is equal to 3 to the x. Each one of these positions is now important. We have the base, which is the 3, we have the power, which is the x, and we have the result, which is y. An exponential function is visualized as follows. on a Cartesian plane, we would have an exponential graph heading up like that. Again, we would be able to say that we knew that it was going to be mirrored on the y equals x line, and so its inverse would be the line that comes down here, where every point is mirrored equally. The inverse of an exponential function has its own name. If this is an exponential, the inverse is called a logarithmic graph. Logarithmic graph. So therefore, the inverse of an exponential function must have the word log in its name. And so you'll see this often on your calculator. What we will do is follow the rules we've always had. We want to swap y with x because y equals x. And so if I write x equals 3 to the y, I need to be able to detach the power. This isn't a square root or a y root. It's actually by taking the logarithm. And we write log on both sides of the variable. So log x equals log of 3 to the y. What logarithm allows you to do is detach the exponent from its base and write it as a coefficient. That means that the number up here can come down and be written in front. So we will write it as follows. Log x equals y times log 3. Now what I can do is use the normal rules of BODMAS and detach the y from the log 3. I could write that log of x divided by log of 3 is equal to y. And later on we will see that this could be simplified even further. We could show that log of x divided by log of 3 could be written as log base 3 subject x. So our inverse of a log graph is written as follows. We will be doing a lot more log work in the next section, so please don't feel uncomfortable. This was just to show you some of the algebra. We will spend a lot of time on logarithms coming up shortly. We've spent a lot of time now speaking about the algebra. Let's just get our head back to some of the theory. Question: every function has an inverse function. Another question: if f of g of x equals x and g of f of x equals x, then g is the inverse of f and f is the inverse of g. Answers: every function has an inverse function is false. Not every function has an inverse function. Usually they are relations. B, if f of g of x and g of f of x are both equal to x, then they are inverses of each other. This is true. More questions. The range of f is equal to the range of its inverse if f is a one-to-one relation. Question. The range of f is equal to the domain of the inverse if f is a one-to-one relation. This is false. The range of f is equal to the range of its inverse in a one-to-one is not true. The range of f is equal to the domain of its inverse is true. I hope that you've understood the basics of inverses. We will be doing a lot of practice in the worksheet that you'll be doing today with an understanding between how to find the inverse, sketch the inverse, and speak about its domain and range, and possibly restrict the original domain. We will be moving on to logarithms in the next section.